What if everything we know, every star, galaxy, planet, and cosmic rule is only a tiny fraction of reality? Imagine standing at the edge of everything science can see and staring into the unknown. Beyond that edge, there are no telescopes that can reach, no satellites that can scan, no light that has ever returned. It's not just darkness, it's a question mark big enough to swallow galaxies. We call it the unobservable universe, a realm beyond the 93 billion light-year wide bubble we can detect. But what lies beyond it? Is it more of the same? An infinite sea of galaxies? Or is it something else, entirely? Something stranger, older, deeper than anything we've ever imagined? Today, we step off the edge of the map and into the abyss of the unknown. What if I told you that everything you've ever seen in your life, every planet, every star, every galaxy is part of just a small, cosmic bubble? A bubble, not of matter, but of perception. This bubble is what scientists call the observable universe, and beyond its limits lies a vast unknown that we may never fully understand. The universe is huge, unfathomably so, but even our most powerful telescopes can only see so far. Why? Because the universe has a speed limit, and that speed limit is the speed of light. Light travels fast about 300 kilometers per second, but it still takes time to cross distances. The farther away an object is, the longer its light takes to reach us. And since the universe began around 13.8 billion years ago, we can only observe objects whose light has had enough time to travel to us in that span. That defines our horizon, the maximum distance we can see. But wait, it gets stranger. That distance isn't 13.8 billion light years. It's over 5 billion light years in every direction, making the observable universe a sphere about 93 billion light years wide. How is that possible? Because space itself has been stretching since the Big Bang. While a galaxy might have emitted its light billions of years ago, the space between us has expanded so much that it's now far farther than it once was. Let's imagine it visually. You're standing in the middle of a vast, dark ocean. You shine a flashlight, and the beam only travels so far before fading. Everything outside that beam is invisible, not because it doesn't exist, but because you can't detect it. That's what the observable universe is. It's not the entire universe. It's just what we can measure with light. The real universe? That could be hundreds, thousands, or even infinitely times larger than what we see. The observable limit is defined by a concept called the cosmic light horizon. Farthest distance light could travel in 13.8 billion years, accounting for the expansion of space. But that light horizon is not a wall. It's not the edge of existence. It's just the edge of visibility. There could be galaxies, clusters, superclusters, even entire cosmic structures well beyond our reach, and we'd never know they exist. Their light will never reach us. Not now, not ever. Our current understanding of the observable universe is built on precise measurements. We know its size thanks to data from missions like the Planck spacecraft, which map the cosmic microwave background, CMB, the oldest light in the universe, a glowing echo from just 380 years after the Big Bang. This radiation surrounds us in every direction and serves as a snapshot of the early universe. It's like a baby picture of everything that exists. But here's the catch: it doesn't tell us what's beyond it. It only shows us what was visible to that ancient light as it was emitted. The edge of the observable universe, then, is like a foggy mirror. It reflects what we can see, but hides everything that lies past the curtain. Now let's talk numbers. Inside the observable universe, we estimate there are about 2 trillion galaxies. Each of those galaxies can contain billions to trillions of stars, many with their own planetary systems. That's more stars than grains of sand on every beach on Earth. It's a cosmic ocean filled with wonder quasars, black holes, nebulae, pulsars, and structures so massive they stretch across billions of light years, like the Hercules Corona Borealis Great Wall. And yet, all of that, every bit of it, is just what fits inside our light bubble. Beyond that, nothing has ever reached our eyes, but the mystery deepens. Not only are we limited by the speed of light, but also by the fact that the universe is expanding and accelerating due to something called dark energy. That means the farther something is, the faster it's moving away from us. Some galaxies are already receding faster than light, not because they're breaking the speed limit, but because the fabric of space itself is stretching. These galaxies will never be seen. Their light is redshifted beyond detection. Even if they exist now, they're gone to us forever. The horizon is not just a limit of the past, it's a frontier that's shrinking what we can see over time. So when we say the universe is 13.8 billion years old, that's not the same as saying it's 13.8 billion light years wide. The actual distance to the farthest observable objects is over 46 billion light years, because the space between us and them has been growing all along. Think of it like dots on a balloon. If you inflate the balloon, the dots move apart. Not because they're moving on their own, but because the surface is stretching. That's how our universe behaves. This leads us to a profound realization. The observable universe is observer-dependent. If you were on a planet in a galaxy 10 billion light years away, your observable sphere would be centered there, not here. You'd see parts of the universe that we never can. And from your viewpoint, Earth might be at the very edge, not visible at all. This means no one place has a privileged view. Every location in space has its own version of the observable universe. So, the full, total universe must be much larger than our visible patch. Potentially infinite. But what does this mean for our understanding of reality? It means that everything we base our cosmology on theories, models, simulations, built from incomplete data. We are blind to what lies beyond, yet we try to imagine it. And in that imagining, the boundaries of science begin to blur into philosophy. Are there galaxies out there with laws of physics different from ours? Is space structured differently beyond the horizon? Are there other civilizations, vast, ancient, maybe billions of years older than us living just outside our range of detection? These questions are no longer confined to fiction. They are part of serious scientific inquiry. But without direct observation, we must rely on models, probability, and the assumption that what lies beyond is similar to what lies within. This is called the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. In simple terms, it looks roughly the same no matter where you are or which direction you look. This principle allows us to infer that the universe continues beyond the observable edge in the same general way, but we cannot prove it. And what if it's wrong? What if the universe is like a bubble in a multiverse foam, and beyond our edge lies another bubble radically different in every way? What if the edge marks a boundary between our reality and something unrecognizable? This is where speculation enters, but also where bold new theories are born. So to summarize, the observable universe is everything we can see, not everything that exists. It's a sphere of 93 billion light-years across, defined by how far light has traveled since the Big Bang, and shaped by the constant stretching of space. Beyond it, possibly more galaxies, more stars, more universes, possibly something stranger than we can imagine. Our vision is limited, but our curiosity is not, and that curiosity drives us to look past the horizon, to try and glimpse what lies beyond. Because if the universe is the greatest story ever told, then beyond the observable edge is the next unwritten chapter. Now that we understand the observable universe is only a small sphere of what we can detect, the next question naturally follows. How much more is out there? Does the universe go on forever, stretching endlessly in all directions? Or is it finite or vast? Yes, but with an ultimate edge. This is not just a question of curiosity. It's a fundamental question about the nature of existence itself. Because if the universe is infinite, it changes everything we know about matter, life, and even identity. Let's start with the science. To determine whether the universe is infinite or finite, cosmologists first look at its shape. The shape of the universe isn't about borders or wall sits, about geometry. And geometry is governed by one key factor: the density of matter and energy. This relationship is described by Einstein's general relativity and measured by something called the critical density. If the actual density of the universe is greater than this critical threshold, space is positively curved like a sphere. This means if you travel in a straight line long enough, you'll eventually return to your starting point. In that case, the universe would be finite, closed, and looped. If the density is less than critical, the universe is negatively curved like a saddle. It would be open, expanding forever, but not infinite in the same sense. Its volume would be unbounded but not endless. And if the density is equal to the critical level, the universe is flat. In this case, space doesn't curve noticeably at large scales. A flat universe implies two possibilities. It could be infinite, or it could be very large but still finite, and unbounded like the surface of a torus in higher dimensions. So what does the data say? Surprisingly, modern observations suggest that the universe is flat, with a margin of error as small as 0.4%. Measurements from the Cosmic Microwave Background, CMB, specifically from NASA's WMAP and ESA's Planck mission support a flat geometry. But here's the catch. These measurements are limited to the observable universe. If the total universe is much, much bigger, then tiny curvatures wouldn't show up within our light bubble. It's like trying to measure the curvature of Earth by looking at your backyard. It's too small a sample to reveal the truth. Flatness supports the idea that the universe is infinite but doesn't prove it. Even a flat universe could loop back on itself in complex topologies. Like a 3D torus, where traveling in one direction eventually brings you back to the start, but without boundaries or edges. You'd never hit a wall, just endlessly orbit the cosmos. And if the universe is infinite, then everything changes. In an infinite universe, matter doesn't just go on. Forever it must repeat. Because with only a finite number of possible particle arrangements and infinite space to arrange them in, eventually those arrangements must duplicate. That means somewhere out there, there's another planet Earth. Another you. An entire galaxy identical to ours. And farther out, a version of you who made different choices. A version who never existed. A version who asked this very question in another language, another form, another cosmic age. This isn't science fiction. This is cosmic probability. But wait, there's more. If the universe is infinite, then it didn't start from a single, small point as we often imagine. It might have always been infinite, and the Big Bang didn't happen at a point, but everywhere at once. Think of it this way. Instead of the universe expanding into something, it was space itself expanding everywhere, stretching, cooling, evolving. The balloon analogy works again, but with a twist. We're not the surface of the balloon, we're points within it, and the balloon is infinite in every direction. It's space itself growing, not expanding into pre-existing space. And yet, even in this model, we still hit a wall of mystery. Because we can only ever see a small patch, we can't know with certainty whether space continues forever or folds in on itself. To crack this mystery, scientists turn to cosmic topology, the study of how space is connected on large scales. If the universe wraps around itself, we might detect repeating patterns in the Siemba, sort of cosmic hall of mirrors where galaxies and radiation echo across space. These repeating patterns would be like cosmic fingerprints, proving that space is finite but unbounded. Some researchers have searched for these patterns. So far, no conclusive results. Another possibility comes from the theory of cosmic inflation, the idea that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of rapid exponential expansion. This inflation stretched space so much that any initial curvature would now appear flat, just like a tiny patch of a balloon looks flat to an ant. Inflation also predicts that the universe should be much larger than the observable region, possibly infinite. If inflation is correct, then we're just seeing a tiny piece of a much larger cosmic puzzle, a puzzle that may never be fully revealed. Still, some scientists propose the universe might be finite, but very large. So large, in fact, that we could never detect its boundaries or looping nature. Even light, traveling for billions of years, might not have made the full trip around such a space. In that case, we'd never know. Our horizon would remain our limit.